Hello everyone, I welcome you all in this lecture. So in this lecture, we will be talking about aircraft model in loop simulation. So this is a very important phase in any flight controller design process. So we will study this in this class, okay? So by the definition, here in a simple language, I can explain to you. Let's say if you want to design any flight controller. So in mill phase, both aircraft as well as controller will be as a mathematical model and will be implemented in any kind of software like a MATLAB and Simulink, where both controller and aircraft model will be sitting as a mathematical model. So there is a no hardware will be involved at this stage. Although hardware model can be modeled in the Simulink but not as a real one. Okay. So there is a no real hardware. That is why the word is real hardware. Okay. In a Simulink, you can model the hardware like delay, etc. But there will be no real hardware is involved at this stage. Okay. So that is how what I have told you. The definition is written. Model in the loop simulation is a software-based simulation approach where both aircraft dynamics and controller are implemented as a mathematical model. Like I said, both aircraft and controller will be sitting in the MATLAB and Simulink or any other simulation software as a mathematical model. Okay, definition is clear, right? Now, before proceeding further, I would like to highlight the clear-cut difference between mill, sill, hill, okay, and flight test, because a lot of people has confusion between mill and sill, and as well as mill versus sill versus sill. There is a common confusion created. Okay, so as I said, controller press ka both as a model mill, clear, right? But what do you mean by the sill? I mean, to sill is also some kind of software in loop simulation, right? Mill is a model in loop simulation. Sill is a software in loop simulation. But here, whatever you have written the code, here also both mathematical, both controller and aircraft will be sitting as a mathematical model. But what is the difference then if you compare with the mill? So here, whatever the controller code you have written in Simulink, you have to compile and you have to convert into the standard language like C and C++, and you have to put the embedded constraints, logic, so that the code can be executable. Okay, and that code you can actually deploy in the real hardware and you can fly the aircraft. Okay, so that means you have to compile the code in C or C++. Okay, so that is a basic difference between mill and sill. Okay, so aircraft, the code should be compiled, logic should be included, and embedded constraint has to be put. Okay, now in hill simulation, aircraft will be as a mathematical model, but controller will be real controller. So in real controller you can put the compiled code. So the controller part will be outside, I mean to say, like a hardware, and still the aircraft model will be sitting in a Simulink or any other software as a mathematical model. And then flight test. So in this, the aircraft becomes real only. So real controller, real aircraft, that is what flight test. Okay. So that is a difference between these mill, sill, hill, and finally flight test. All right. So what is the purpose of the model in loop simulation? So see, if you are writing anything, code, etc., in a MATLAB Simulink, let's say, so you can analyze the aircraft. You can see how my aircraft is behaving naturally or as well as during the force response. And then validate the controller at the early design stage. I mean to say, let's say if you have taken the model with high fidelity, and then you can actually design the controller and you can actually test the controller, design controller in a MATLAB and Simulink with the aircraft which you have considered, okay, taken, okay. And then if any the other non-linearities is there, then you can actually study, like for example, if you are landing the aircraft, you can actually model the ground effect model, or if you are designing a VTOL, you can actually have a non-linear effect during the transition. So these things you can actually model, you can test. Okay, and of course reduce risk before hardware testing. So since there is no hardware involved in mill, so whatever you can do in the software only, and whatever the results is coming, you can actually correct based on the desired result. If you are not getting, you can tune the results, you can change the parameter, you can actually have so many analysis you can do. Okay, so there is a cost effective one. Okay, and what is the typical mill architecture? So aircraft model will be there and controller will be there. Two things is common. Okay, and depending upon the configuration, whether it's multi-rotor, fixed wing, or hybrid. Okay, and then of course aerodynamic model and propulsion model, and control system model, sensor actuator models. Because in a simling, what you can do during the mill, you can actually model the sensor, you can model the sensor noise, you can model the actuator, first order, second order, all things you can do here. Okay, and of course one environment you should need like MATLAB and Simulink in order to do your mill. What is a typical block diagram? See, you are commanding something, right, and you want to get value. Let's say for example theta 5 degree you are commanding, 10 degree you are commanding, you should get theta 10 degree, or velocity you are commanding, you should get the velocity. Okay, so whatever the output is coming from the aircraft, you should compare in order to find the error and to give the controller, so that controller can correct, and finally whatever you want you can achieve, right? So here this is a typical controller architecture. There is a command outputs, controllers, aircraft models, output, there will be sensor, and here it is written feedback loop closest through the sensor model in the software. If in a first stage you cannot consider, I mean to say, sensor, you can directly provide the feedback, but at a later stage you should consider the sensor model. Okay, so this is a typical mill block diagram. Okay, okay. So what are the components in the aircraft model? Like first, obviously equations of motion, because in reality how the aircraft is behaving, you have to model mathematically, right? So equation of motion is needed, and all this equation of motion, controller, everything I have covered in the previous lecture in this course. Okay. Aerodynamic force and moments model, propulsion system model, and environment disturbance. Yes, that's the important part. Environment disturbance. This is the equation of motion is needed. Yes, aerodynamic model is needed. Both force and moment model, and propulsion system model is needed. Okay, and then environmental disturbance like wind, okay, continuous wind, and then turbulence. Then if you approximate the turbulence, you will get the gust. Okay, so wind, turbulence, and when you approximate turbulence in a discrete fashion, you will get the gust. So wind, turbulence, gust, as atmospheric disturbance you have to model. Okay, so that you should be ensured that the design controller is able to reject those disturbance. Okay, and wind shear also you can model. Okay, and this stage you can do the Monte Carlo simulation also, where you can put up all the aerodynamic models, geometrical models simultaneously, and you can actually check the robustness of the controller, because whatever so far you have method you have found out the aerodynamic model using CFD or using analytical approach or both, that is not 100% accurate. So you can do the Monte Carlo simulation, you can put up, you can see how much controller the perturbation it can handle. Okay, CG variation, etc. Okay, and then controller in a mill can be designed using different approach: PID, LQR, linear quadratic regulator, proportional integral derivative controller, linear quadratic Gaussian, non-linear dynamic inversion, and this is sliding mode controller, and this is incremental non-linear dynamic inversion, and this you can make adaptive controller or robust controller. Okay, and finally when you have a design the controller at different operating point, if you combine all the controller, that is the, I mean to say, the gain can be scheduled based on the speed square or dynamic pressure. So overall control architecture, even though if it is a linear at a one particular trim point, but overall so many controller you have designed, so overall control architecture will be non-linear only. Okay, so non-linear controller, and if you are using INDI or NDI, actually at the it can operate, the same controller can be operated in multiple trim points. Okay, already I explained to you. Okay, and there is some kind of switching logic from vital to transition and then backward transition. Okay, so you can actually, these things you can actually model. Okay, and what will be the advantage of mill? Of course, fast and low cost, because everything is in software only. And then a safe testing environment. Yes, it is of course safe. So whatever you can model, sensor, controller, in aircraft model, if you want to change anything, if you want to include non-linearity like ground effect, rotor interaction with the wing, anything you can model in the simulink and you can actually test. So safe testing environment. Okay, and easy tuning and debugging. If anything is wrong, you can actually debug. Okay, and if you are changing the operating condition, and if you want to analyze the aircraft, or if you want to include some additional part in the aircraft model, so you can actually, based on the changes, you can actually tune the controller, and based on the, if you want to change your desired response uh, uh, criteria, for example like a settling time, overshoot, etc., you can actually easily tune based on the requirement. Okay, and if you do this mill, then of course it is a good for controller development. Okay, so in next stage, if this is successful, then you can go to the sill, and then finally hill, and then flight test on a scale model, and then you can expand the envelope. Okay, and what is the mill limitation? Okay, of course, what is the accuracy? Because whatever you are modeling, like aircraft model, okay, that is not 100% correct, and the controller gain, because you are analyzing the aircraft, right, and you are designing the controller based on this response only, and this response is coming, which is the aerodynamic model, propulsion model, you have designed, you have found out, okay, using this model. So okay, if this is an inaccurate, so the controller which you have designed will also have a inaccuracy. So that means accuracy is a problem in a mill. Okay, because let's say this is the aircraft, you have model in the simulink and your controller model in the simulink. So in this aircraft, aerodynamic model, propulsion model, all the model is sitting, and if the modeling is incorrect, so this model which you are analyzing, based on this response you are designing the controller, so that also will be incorrect, because this is a model dependent controller, right? So accuracy is a one of the problems. Okay, highly depends upon the model fidelity. Does not capture the real hardware delays. Although you can actually, using Pade approximation, as I explained, you can actually model the delay, actuator dynamics. You can actually put the physical limit constraint on actuator in the simulink. But whatever you will do, you will have some kind of problem, inaccuracy. Okay, so does not capture the real hardware delays. Okay, and of course, in reality, sensor will behave in a very different fashion. Okay, so the cannot fully represent the real sensor noise, I mean to say noise, etc. Okay, but whatever the possible, try to model in a simulink as accurate as possible. And what is the application? Any aircraft, spacecraft can be designed, flight controller can be designed. Okay, that is the best application, right? Not only normal, but in off-normal flight phases also, like in case of any upset condition like high angle effect, flight dynamics, or any kind of fault terrain scenario where aileron got stuck. Now you have to take that, you have to counter, you have to, uh, I mean to say, the aileron is failed. So whatever the job is aileron is doing, you have to use in some another way. Like you can roll, for example, using differential elevator here. Okay, and then if the rudder is failed, then you have to counter the yaw using aileron or spoiler, using drag difference. That means if any fault train scenario is there, let's say one engine is failed, so you have to use the another engine to land the aircraft safely. Okay, so in the fault tolerant condition, the mill can be used. In the software, you can actually check this fail scenario. Okay, and the conclusion is, of course, this is the first step to design a flight controller. So model in the loop simulator is a critical first step in the aircraft control system development, enabling safe, fast, systematic validation of the control history before real world testing. So in a sim you have to, or any other software, you have to model everything, aircraft, in aircraft all the non-linear model or other effects, and in controller you have to model everything, sensor noise, hardware delay model, I mean to say. So everything you can actually model, and once it is ready, the code is ready, simulation is running, then you will complete the first step for a controller design. Then once you satisfied based on the standards, there is a standard in controller design, mill standard. If you satisfied those standards, then actually you can move towards the software in loop simulation, and then hill simulation, and then finally flight testing, not the full aircraft but small scale model. And then once you satisfied, then you can actually spend the left, you can go for a bigger size aircraft. Okay, so we'll continue here from the next lecture. Next lecture I will show some model loop simulation architecture which we have developed in the MATLAB and Simulink. Okay, we'll discuss more. Thank you so much.